So, do you guys remember when I say I walk in one day and give +5 to whoever is in the room?
Yes.
Should I be mean and do it today?
Yes.
No, it's Thanksgiving, but I just want to remind you that it's coming. One of these days I'll just walk in and say +5 to whoever is in the room. But some of you are not here today, and that's fine. It's Thanksgiving, so I'm not going to do this. Okay. So before we start, if you have completed the pH and titratable acidity, please give it to me. This is again as a +5 credit, and there are going to be quite a few of those left. So the one here, fact characterization, practice problems, again it's 5 points extra credit. So it's kind of encouraging you to do this homework, but you are not obliged to do it. If you do it, you get extra credit, and it helps with studying. So it's right there for you. It's due next Wednesday, not on Monday. So you have not to worry about it over break. Okay, and I will unhide the pH and titratable acidity practice problems. I'll just give you guys some time to turn it in by 5 today, if you are planning on turning it in, and then I will unhide it so that you can see the key for the problems. Okay, so moving on to a new topic, and it will be the topic of your lab next week. Fat characterization. Let's see what you know, if you know. What is true here? Which of these statements are true? You think. I don't expect you to know. This is the topic of this section, but let's see. Peroxide value used to detect advanced stages of lipid oxidation. Hexanal gives an indication of an advanced stage of oxidation. Iodine value can be used to detect oxidation. Do you have any idea at least? Okay. Michelle?
A and C.
Okay. Anybody else want to guess? Ben?
A and B.
What did you want to say, Sarah?
I'll go with B.
You go with B. What did you say, Ben?
A and B.
Huh. Anybody else? Yes, Michelle?
B and C.
Did I say, you're Michelle?
Only A.
Huh?
Only A.
Only A. And you said B and C? Why? You were just guessing. Yeah. Well, you guessed right. It's just B and C. So peroxide value is actually a measure of the initial state of oxidation. So lipid oxidation is mostly an auto-oxidation where a radical is formed. It's the hydroperoxide that is formed, and then for a propagation of the reaction. So peroxide is the initial stage of oxidation. Hexanal is secondary metabolite of oxidation, so it is a measure of an advanced stage of oxidation. Iodine value is a measure of degree of unsaturation, but if a fatty acid got oxidized, it will lose the double bond, and therefore it can be measure of oxidation as well. So if it starts off with a specific iodine value and that iodine value decreases, that means there is a sign of oxidation. So B and C are correct. And we'll talk about each one of those in more detail. Have you heard of saponification value before? You did? Okay. So
I don't remember anything
You heard about it, but you don't remember it. Okay, we're going to cover it today, and the answer to this is false. It's not a measure of fatty acid saturation. It's actually a way to determine the molecular weight of, or the average molecular weight of fatty acid, and it's kind of an identification for authentication identification of a particular fat or oil. Okay, can you list some of the importance of fat characterization, and what do we mean by fat characterization? It's not specifically quantifying total fat. What is meant by fat characterization, and why is it important in food analysis? Can you give anything, Andy?
For nutrition label, you need to ensure that there's no trans fats in your food. It's also beneficial to label saturated and unsaturated fats.
Very good. So fat characterization, part of it is looking at the different categories of fat. Do you have saturated, polyunsaturated, and do you have trans fat? Due to hydrogenation of the oil, you can generate trans fat. Okay, so that's one thing, nutrition label. What else? So that is the nutrition label, and I pressed too soon. I should have done that in multiple stages. What did you see? What did you see? What was fast enough to see?
Shelf life stability.
Yes, so shelf life stability. So if you have a high fat content in a product, or even a low fat content in a product, doesn't matter, and you abuse the way it was stored, you have oxygen, you have light, and you have temperature and moisture abuse. So you will end up with having an oxidative rancidity. And if you have enzymes in there, like lipases, you have something called, what type of rancidity? Ben? Hydrolytic rancidity. So you have the oxidative rancidity and you have the hydrolytic rancidity, which is basically breaking down your fats into free fatty acids. And free fatty acids will have off flavor, and free fatty acids are actually more prone for oxidation than triglycerides. So the rate of oxidation of free fatty acid is faster than the rate of oxidation of triglycerides. What else did you glance? That was too quick, right? Yeah, let's look at those. Okay, so processing effect. So like I said earlier, hydrogenation of oil to make the vegetable butter or margarine. So in hydrogenation, you're actually changing the degree of saturation. So you measure, as a measure of how efficient your hydrogenation process was, you can measure iodine value before and after hydrogenation. So you can determine how much were you able to hydrogenate the oil. Another, the trans fat. So upon hydrogenation, the cis form will convert to trans form. So you want to monitor that, an effect of hydrogenation, how much trans fat you have produced or not. Palatability and sensory effect. So it's like spreadability of the butter, how much you have total solid fat index, which has to do with how smooth the mouthfeel is of that particular fat. Safety, some secondary metabolites are toxic or they're mutagenic. So they're right. I'm ahead of myself. Malonaldehyde and cholesterol oxide, these are mutagenic, carcinogenic. So we talked about nutrition labeling, saying saturated, unsaturated, trans fat. Of course, cholesterol is another important component. Talked about shelf life. And then also in development of food ingredient composed of lipid. For example, olestra simulates fat, but it does not digest it as fat, and it's basically a sucrose with at least several, like 6 to 8 fatty acids. So the R is a fatty acid chain. So it has the characteristics of a fat, but is not bioavailable. So, and it doesn't contribute to your 9 calories per gram. So I want to talk a little bit about processing effects. We talked about production of trans fat because of hydrogenation. Another fat characterization is important when you're doing deep frying. And in industry, when you're using deep frying to produce a snack product, very important, or fries, that you would get frozen fries or fries in McDonald's or anywhere. So there is a limited amount of time that you can use the oil for frying. Because when you fry, there is from the potato, let's say water can be that seep out of the potato, and with temperature, then you can end up having hydrolytic rancidity. So that means your oil will break down, not necessarily an enzyme. You have water and heat, and that will cause breakdown of the triglycerides and production of free fatty acid. And the free fatty acid will have an off flavor and will get oxidized. So you cannot continually fry the same oil for an extended period of time. So to monitor the quality of the oil, you measure free fatty acid, for example, content of that oil over time, and then when it gets to a certain point, say, well, it's time to change it or add fresh oil. Oftentimes they add fresh oil. Probably not ideal. So yeah, hydrogenation, we talked about, you want to make sure to not produce trans fat, but at the same time monitor the effectiveness of hydrogenation, and you can monitor that by measuring iodine value. Refining. So a lot of time your crude oil has free fatty acid in it. And then refining, it kind of clarifies that or remove the fatty acid. And usually you do that with an alkaline step here, alkali refining. So you neutralize those fatty acids and you produce soap, and you centrifuge and you remove that from the oil. So, and then you want to test that by measuring free fatty acid before and after refining. Winterizing is another process that you would do for the oil, and it's basically getting rid of any components that would crystallize. So if you're making a dressing, salad dressing, and you put it in the fridge, you don't want it to be cloudy at a certain time point. You want it to remain clear. So your oil needs to be winterized in order to remove these crystals. And during processing, winterizing step is just chilling the oil, cooling it down, so any solid material may crystallize and precipitate out of that. Then you will have a winterized oil. And you do test that winterizing by doing a cold test or a cloud test. Bring that oil to a cold temperature and then see if any crystals form. If crystals form, that means your winterizing step was not efficient enough. And clouding is very related test where you also gradually heat the oil and you gradually cool it down, and then you monitor at which temperature you see cloud forming. And that would be an indication of how well the oil was winterized. We talked about mouthfeel and taste, and it's directly related to spreadability of the butter, how much solid fat content you have in your fat. And also the taste of it. It also depends on the hydrolytic and oxidative rancidity and how much free fatty acid you have in your non-refined oil. And this is the safety due to secondary oxidative metabolites. So there are a lot of different analytical methods to characterize fats. You have a whole list of physical characteristics. We'll give some few examples. And then you have the iodine value, which is the degree of unsaturation. Saponification value is authentication, and you can determine average molecular weight of the fatty acid. And free fatty acid is an indication of refining as well as an indication of hydrolytic rancidity. And these usually are done on bulk fats and oil. That means, the fat and oil, not the fat and oil extracted from a food product. We're going to talk about how do we assess the lipid oxidation, the present state. That means now the state of the oil right now in terms of oxidation Or evaluating the stability, how long this fat or oil can be stable, what's the induction period, the period before the oil gets oxidized at a particular, under particular condition in the presence of antioxidants. This is also very useful in industry when you're determining the effectiveness of an antioxidant, whether it's a natural antioxidant or a synthetic antioxidant. So you would determine the onset of oxidation with and without that particular antioxidant that you're formulating with. And then there are different chromatographic methods for the characterization of how much fatty acids you have, free fatty acids, trans fat, cholesterol, unsaturated, saturated, so you can assess that. All right, so this is a summary of the methods. There are analytical method consideration, of course, is first of all, if you want to assess the oxidation state of fats within a food matrix, you want to extract the fat first in order to determine its peroxide value or determine its secondary metabolite like hexanol. So the first step is to extract the fat if you're not working with the bulk fat or oil material. So to do that, you use solvent extraction. Oftentimes it's a combination of couple of solvents, so you make sure that you extract the polar and non-polar lipids, and then you remove the solvent by evaporation and you carry out that test. This is what Amy does most of her time in the lab. What combination of solvents do you use, Amy?
I use the one who are on the data, like your
Okay, not listed here, but yes, we did that in the lab for the Muginer, where you have a little bit more polar solvent and a non-polar solvent. And so yeah, so the first step of looking at lipid oxidation or lipid hydrolysis is extract the fat. Another important consideration is when you are preparing the sample or extracting the fat to determine oxidation, you want to make sure that your sample preparation does not induce further oxidation. So you want to make sure that the way you are extracting does not allow the sample to be exposed to oxygen or abusive heat, temperature, and light exposure. So oftentimes you make sure you flush with nitrogen, you make sure you are working in subdued light, and also cool temperatures when you're extracting and preparing your sample. So these are main considerations for that. Okay, so I will go over a little bit of physical characteristics method. They are explained more elaborately in your textbook. It would be nice to read for FYI. But a refractive index, for example, is a measure of the refraction or diffraction of light when the light hits a surface of, let's say, oil, and then it will refract, basically change angle. So this can be helpful in a measure of degree of saturation or unsaturation. It's also an authentication, and it's very particular to the oil. So every different oils have different refractive index. So it's kind of an ID or identification. Melting point. It's pretty obvious what you're looking for. Different fats and oils melt at different temperatures. The smoke, flash, and fire point, this is interesting. This is important in, especially when you choose oils for frying. So you never want to fry in olive oil, for example, because olive oil have very low smoke point. That means that at temperature at which it starts to smoke, and then it will ignite, and then fire. And then I have a story to tell you. The story when I almost burnt my house down. You know how I always, you don't know, but I'll tell you. I love fried food, so we always deep fry stuff at home. So I put a pan with lots of oil in it on the stove and went down to do some work on my computer, and all of a sudden the fire alarm went off. So instead of telling my daughter to leave the house, I told her, lock yourself in the room. And that's the first thing that I did bad. Second thing, what do you think I did with the pot that the fire is coming out?
Oh, she had water.
I opened the faucet on the oil and fire. fire. See, you can't think straight, and there's almost burning the house down. So I did an explosion, so boom, in my face, on the ceiling, all black. Okay, what do? Didn't end there, still on fire. So I took the pot. Good thing was that there was snow outside. So I opened the door, threw it in the snow. Another explosion outside of the house. So after that incident, Cindy determined that I'm a walking hazard, so she bought me a deep fryer that is electric. So I no longer make fires anymore at home. But I still deep fry food. But anyway, that story told, it's very important to select the oil for different purposes and watch that you don't get to a fire hazard. So the cold test and the cloud point is basically testing the winterization efficiency of your oil. So cold test, that means you cool the oil to 0 degrees and leave it there for a few hours and watch to see if there are any crystals formation. If there are any crystal formation, that means the winterization step was not done properly. The cloud point is actually determine the temperature at which you can see those crystallization start to occur. So you would heat the oil first and then gradually reduce the temperature and record the temperature at which you see cloud and you don't see the thermometer anymore in your oil. The solid fat index, as well as consistency and spreadability, it's directly related to the mouthfeel and spreadability of your solid fat. And this can be determined by NMR, solid fat index, and this has a texture analyzer probe that you would use to actually determine the consistency and spreadability. So these are your physical characteristics test. Like I said, there are more elaboration in your book chapter that you can read. Okay, so methods for bulk fat and oil, we'll start with iodine value, and like I said, it's a measure of degree of unsaturation. So what you need to know is everything on this slide. So it's very important that you know that the iodine value is actually grams of iodine by 100 grams of sample. You need to know this definition, okay? So grams of iodine absorbed by 100 grams of sample. The more the sample has double bonds, the more your triglyceride have double bond, the more it's going to absorb iodine, okay? So here's the reaction that you will carry actually in the lab next week. So you will have your oil. You might have a double bond, mono or polyunsaturated fatty acids in your oil, or you may have very limited amount of those. So the principle of the method is you have, you mix it with excess iodine chloride, and then you will form, you break those double bonds because iodine will be taken up by the double bond, and you will have a remaining iodine chloride. Then you titrate the remaining iodine chloride, or you mix it with potassium iodide, and then you get iodine. Okay? So you mix the excess or remaining iodine chloride with potassium iodide, and you get iodine. The iodine, you add an indicator, in this case is starch, because starch with iodine will give you blue color. And then you titrate, here's where you titrate, with sodium thiosulfate. Okay. So you titrate with sodium thiosulfate, this sodium thiosulfate will take up the iodine, and then you will end up with a colorless solution because the iodine now is part of the product. So it's taken up, so you lose the blue color. So in iodine experiment next week, you'll be titrating to lose the color. So to an endpoint that is colorless, basically. All right, so the way you calculate iodine value, it's the same derivation that we talked about for at equivalent point last time for titratable acidity. Same principle of deriving to get the equivalence of an acid equivalent to a base, but here the equivalence of iodine equals the equivalence of the sodium thiosulfate. Okay, so here you have I2 and here you have 2 moles of the sodium thiosulfate. So at equilibrium, N by V of this equal N by V of that, and then you follow the same derivation we talked about last time to get the iodine value, and since it's a percentage per 100, you multiply by 100, and also you correct for milliliter to liter, okay? So it's, and this is your molecular weight, the molecular weight of your iodine, okay? The 126.9 is the molecular weight of the iodine. So why is it blank minus sample? So you have to always titrate a blank where you don't have your oil, you just have everything except the oil. So why is it blank minus sample rather than sample minus blank? Yes, Sarah?
Because the blank one has more iodine because the is absorbed
By the fat. Very good. So yes, because you won't have fat, so you all of your excess, everything you put in here will remain, and you will have the highest amount of iodine generation. And therefore your blank volume of sodium thiosulfate, when you titrate the blank, will be the higher volume than your sample. The more unsaturation you're going to have, the lower the value of ICI, the lower iodine, and the sample volume will be lower. Okay, and then the difference will be higher, and that's why you will have a higher iodine value. Okay, so kind of inversely proportional to the amount of double bonds that you have. Okay, do you want me to repeat that? Yeah? Okay. So the more unsaturation you have, the less remaining iodine chloride you will have, because more will be absorbed by the double bonds. And less you have, the less production of iodine. The less production of iodine, the less the volume needed to titrate the sample. Okay? And therefore you'll have a higher iodine value. Okay. So it is used as fat characterization. That means every original oil will have its own iodine value, and that would be an authentication kind of value. You will use it when you are monitoring hydrogenation process, and it can be an indirect determination of oxidation. So 3 different uses for iodine value. Yeah.
So is there a database of fat characterizations
Yeah.
for that? Okay.
Yeah, so there is actually, I don't have the book, there is a table in your chapter with the different values, iodine value, saponification value, refractive index for different oils. There is a database, yeah. Okay, now that Joshua is left, do we give the +5 now? No. Okay. Saponification value. Don't tell him I said that. It's on the recording. Yeah, I think so. I'm not going to post it, no. Okay, so saponification value is again used as an authentication, as well as you can use it to determine the average molecular weight of your triglyceride in the sample and the most abundant fatty acid in your sample. And we're going to go over these calculations that you're going to love so much today. Okay, also you want to know this. It is defined as milligrams of potassium hydroxide required to saponify 1 gram of sample. Again, this is important that you know this. So basically the principle of the experiment that you're going to do in the lab is you have your triglycerides, which is composed of 3 fatty acids plus glycerol, and it's a condensation reaction. So when 3 fatty acids and a glycerol are formed, 3 moles of H2O is released. Okay, so that is helpful to know for the calculation later. And then you're going to mix it with excess amount of potassium hydroxide, and you'll do a refluxing experiment. They're going to be refluxed for a certain amount of time with heat to saponify, something that is equivalent to what you did in the fatty acid determination lab, where you are freeing the fatty acids from the glycerol backbone. So you end up with glycerol, potassium salt of fatty acids. Okay, so you mix it with excess potassium hydroxide, and the excess, what remains after the saponification, so some potassium will be taken up by the fatty acids, and some OHs will be taken up by the glycerol, and then you will break the bond that way, but there will be remaining KOH. The remaining KOH is titrated with HCl. So it's a base, so the titration here is with HCl. You have phenolphthalein indicator, and at the end point of the titration, so you are starting with a base.
Pink to clear.
Huh?
Pink to clear.
Pink to clear. Thank you. Okay. So it's opposite of what you did in the lab, clear to pink. You're starting with a base. You titrate with an acid in the presence of phenolphthalein. Again, your end point is a clear point titration. Okay. Again, here it's blank minus sample, and it's the same thing, because your blank, you're going to run a blank, you won't have triglyceride in your blank. So all of your excess KOH, everything, you need to titrate. So your blank will be a higher volume than your sample, obviously. So the more moles you have per gram of fat, the more number of moles per gram of fat. This is very important. The more number of moles you have per gram of fat, the less is your volume of your sample. So if you have a very, very large fatty acid compared to a very shorter chain fatty acid, which one will have more moles per gram? The smaller, because you will have more of that to get to 1 gram. So this is important to know, because I always like to ask this one question. If you have higher saponification value to another oil that has lower saponification value, which one will have a higher molecular weight? You just answered that question. If I have a higher saponification value for oil A and lower saponification value for point B or oil B, which one would have a higher molecular weight? Goodbye. Happy Thanksgiving. You just answered this question. How many moles? Huh? B, thank you. Yes. So the larger fatty acid will have less number of moles, so you will need less to titrate. That means you will get a lower saponification value. Okay. So since it's milligram per gram, so you'll notice here it's the same equation, but you do not convert to liter. You do not divide by 1,000, and you do not multiply by 100, because it's in a gram, not in 100 grams. So it's basically the same equation. Here it's the molecular weight of KOH. Okay? Yeah?
Say that again, I'm sorry.
Which one?
So the more number of moles.
Yeah, so the more number of moles you have, that means more KOH will be absorbed, right? Because if you have more in 1 gram of fat, in 1 gram of fat, if you have more number of moles, that means you have, what's number of moles? Let me remind you of that so that you can visually see that. So moles equal weight of your sample over the molecular weight, right? Right? So if your molecular weight is low, small, your number of moles will be higher. Okay? So in 1 gram of sample, and then oil A we said, right? There's oil A and there's oil B. We said oil B has higher, what did I say?
Oil A has higher saponification.
Higher. And this is lower, saponification value. Okay? So oil A has higher saponification value. That means oil A required more KOH, right? Because KOH is milligram of KOH required to saponify 1 gram. So oil A had required more KOH. That means it has more number of moles of this than oil B. This means this is a bigger molecule. If it's a bigger molecule, it has higher molecular weight, that means number of moles will be lower. Okay. All right. So in your book, there are a couple of mistakes which will be corrected in the next edition. If you are a person that goes back to the book, you're going to see a different equation and you're going to say Pam is wrong. No, Pam is right. The book has S minus B. It's actually B minus S. So always the blank is higher because the blank doesn't have this. So you'll have all of the excess. Also, your book in the iodine value does not have division of 1,000. You have to divide by 1,000 because you're correcting for milliliter to liter. In case you're a person that goes back to the book, I'm just pointing that out. Okay, so let's do this. Let's work on this. And I'm going to give you pointers for that.
You want this on paper?
Yeah, how about put it on paper, you get +2 for it.
Oh, check, I'm not sure about that. I have my lab notebook. I got one. I do have paper. It's baby paper. And a little pen. Everything that ever gets shoved. Does not.
Okay, so this is the chemical reaction. You have 1 mole plus 3 moles. Okay, and the given is 190, so their saponification value is 190 milligrams per gram, milligrams of KOH per gram of oil or fat. And then, so this is your chemical reaction, but this is also what you need to remember, that 3 fatty acids plus glycerol will give you triglyceride and 3H2O. So when you want to calculate the molecular weight, you have to take into account the molecular weight of the glyceride, molecular weight of 3H2O. So your calculation should give you triglyceride molecular weight, and from there you plug in the molecular weight of glycerol, which I believe is, it's the molecular weight of glycerol, 92. Molecular weight of water is 8. Okay, so you can then, when you know this, you have these, you can get the average molecular weight of fatty acid. But first you want to get the molecular weight of triglyceride. How can you get that when you have this chemical reaction and this information and that information? General chemistry. Anybody close to the first step, getting the molecular weight of triglyceride?
Is the first step converting for the moles of KOH used?
Yeah, so the first step, you have 3 moles of KOH. You get what is that equivalent to molecular weight. Okay. So basically what this is telling me, it's telling me 190 milligrams of KOH is absorbed by 1 gram of oil. So this I have here, 1 gram of oil is taking up 19T. If I want to convert it to gram to unify the units, it's 0.19 gram of KOH. I have 1 mole of triglyceride. So 1 mole of triglyceride will have an X amount of molecular weight, right? Or X molecular weight. But I have 3 moles of KOH. 3 times 56.1, right? Then I want to solve for Tg. So it would be molecular weight of Tg equals to 3 times 56 yeah, divided, yes, thank you. Divided by 0.19 grams. This is grams per mole. Okay, so this is 1 gram, and here would be grams per mole. Okay, so units will cancel, and then you'll have molecular weight of triglyceride.
885.
Grams per mole. Okay, did you guys get that first step? So this was the given. 1 gram of triglyceride will be, or 0.19 gram of KOH will saponify 1 gram. In the chemical reaction, you have 1 mole of this and 3 moles of that. If I convert this to grams per mole, then I can apply this equation to solve for molecular weight of triglyceride. Okay, so I get now the molecular weight of triglyceride. So I plug that number here. So 3 fatty acids plus glycerol, which is 92 grams per mole, equals 885 grams per mole plus 3 into 18 grams per mole. Then 3 fatty acids equal 885 plus 3 by 18 is what, 54? Yeah? And minus 92. What would that value be? Do you have a number? Huh?
848.
848?
Yeah.
Okay, so then one fatty acid, 848 divided by 3,
283.
86?
83. Sorry.
83 grams per mole is your average molecular weight of fatty acid, and this would be equivalent to a molecular weight, I think, of olive oil, maybe? Not olive oil, oleic acid. Okay, do you have a question? Can you see? Okay. So the next part of the question, if the saponification value was less than 190, would the average molecular weight of fatty acid be less or more? We talked about that, it will be more. Okay. So free fatty acid, like I said, this is a little bit different than the slides. Make sure you add indication of hydrolytic reactivity to your slide that you have. So it is a measure of fatty acid liberated upon hydrolysis of triglycerides. So it is an indication of hydrolytic reactivity, and it's an indication of adequacy of refining. So in crude oil, you have usually high fatty acids, free fatty acid. When you refine them, you reduce that free fatty acid content. All right, since free fatty acids are acids, so you titrate with a base, and basically it's the same as titratable acidity equation, exactly the same. 282 is grams per mole of that particular acid. In this case, we use oleic acid as the main acid, so you use the molecular weight of oleic acid. Okay? And you can convert using conversion factor to different fatty acids. If you want to record it as palmitic, you use conversion factor. There are tables for that. Okay, I'm going to stop here for lipid oxidation. Before you leave, I just want you to know that next week, you know, when I said you're no longer in a group of 5, I lied. You go back to your groups. Yeah, you go back to your groups, and each group will work with one particular oil, and will work on iodine value, saponification value, and peroxide value. That's your lab next week. I'll send you reminders at the end of the week. Okay, happy Thanksgiving, everybody. Enjoy your break.